Hello and welcome to this fourth video on nodal analysis. So over the past few videos, we've taken this circuit and we've written our nodal analysis equation, and this is a circuit which has two nodes. So we always write an equation for all of the nodes in a circuit that are not the ground node. So I've only got one equation here because I've got two nodes, so 2 minus 1 is equal to one equation. And I wrote the equation, current in to our node V0 is equal to the current that flows out of our node V0. And what we did in the last video was we were able to take this equation that we got that had three unknowns, our unknown I1, our unknown I2, and our unknown I0. And instead of representing this just as an unknown current, we were able to represent each of those unknown currents as a voltage difference across a resistor divided by the resistance of a resistor. That's important because every single time you do nodal analysis, that is essentially what you're going to be doing. It'll get more complicated. You'll be dealing with things other than just resistors. You'll be dealing with, inductors and capacitors eventually. But for right now, dealing with just resistors, this is pretty much what you're going to do. You're going to represent that current as a voltage difference divided by the resistance of that element. So now, one last thing I want to say. In this particular equation, because we only needed to write one equation, we had two nodes, so that meant we only wrote one equation. We wound up with an equation that in the last video, we wound up with one equation, and that equation had one unknown. Now, we are going to do more complicated examples eventually, but hopefully you might be able to see if we had three nodes or four nodes in the circuit, like if we had a circuit that had four nodes, we would write three equations because we'd write an equation for every node that was not the ground node. And we would also have three unknown voltages in that circuit. So we would have to solve a 3 by 3 system of equations. And we will work on solving that, and we'll go over a bunch of different ways to solve that. But at any rate, an important thing to realize just at this step in the problem, where we have reduced this down to one equation and one unknown, is you can solve this however you want. At this point, the problem is essentially algebra. However you are comfortable with solving this, or, as is probably more the case, however you are required to solve this for your circuits class, that's how you're going to solve this. But you can solve this in any method. Any method that's going to solve this, that's going to give you the correct value for V0, is going to be equally valid. You can use an equation solver. You can use MATLAB. You can do it by hand. You can use linear algebra. However you want to get your answers, and in this equation we only have one unknown that we're trying to solve for. But when we do more complex problems, we could have three unknowns or five unknowns. That's essentially how you are going to, or you can solve it however you want. It's essentially an algebra problem now. So anyway, speaking of which, after that long introduction, let's just go ahead and solve for V0 in this problem. So now I'm just going to rewrite this. I'm going to get rid of all of these zeros and V0 minus 0, because we know if we subtract 0 here that we're not really changing this, and I can just rewrite this as negative V0. So let me just go ahead and do that. 2 minus V0 divided by 5 is going to be equal to 7 plus V0 divided by 9 plus V0 divided by 7. So now what I'm going to do is I'm going to group all of the constants on one side and all of my V0 terms on the other. So I'm going to be left with 2, and I'm going to subtract 7 from both sides. So I'm going to get 2 minus 7, and now I'm going to add this V0 over 5 to both sides. So 2 minus 7 is going to be equal to V0 over 5 plus V0 divided by 9 plus V0 divided by 7. And now what I'm going to do is I'm going to factor out the V0 from everything on this side of the equation. And I'm also going to simplify this, right? Because 2 minus 7, I can just simplify that. That's going to be minus 5. So this is going to be V0, I can factor out of all of these, and I can rewrite this as V0 times the quantity 1/5 plus 1 over 9 plus 1 over 7. And then what I can do, because I'm looking for V0, I can just divide everything by this whole quantity. And I am left with minus 5 divided by 1 over 5 plus 1 over 9 plus 1 over 7. So minus 5 divided by all of this is going to be equal to my quantity V0. And now I'm just going to go ahead and get out the calculator. So it's set to programmer. Let me set it back to scientific. Okay. So first thing, I'm just going to compute this. I'm going to compute this denominator. So I'm going to take 5 inverse plus 9 inverse plus 7 inverse. So that equals that. And now I'm going to take the inverse of all of that. So I'm going to invert all of that. And I'm going to multiply that times 5. And now I'm going to multiply that times -1. So now I know that my V out is going to be equal to 11.014. So actually, yeah, it's going to be equal to 11.014. I'm going to round that off. So equals, or minus 11.014. So that is going to be my output voltage, my V out for this particular circuit. And let me just go ahead and I am also going to solve for. So I've solved for my V out. I've figured out that my V out is going to be minus 11.014. That's what it was, right? Yeah, minus 11.014. And so now I have to figure out what my I0 is, right? So my I0, it's just going to be, let me write this over here. My I0 is going to be the voltage difference across this resistor, so that is V out, that's the high side of my voltage, minus the low side of the voltage, which is just 0. V out minus 0, V out minus 0, divided by the resistance of that resistor, which is 7 ohms. So if I simplify this, this is just going to turn into V out divided by 7. And V out is minus 11.014 volts. So this is just going to be minus 11.014 divided by 7. And let's just go back to the calculator. And I'm going to divide that by 7. And I get minus 1.753, or minus 1.573 amps. So equals minus 1.573 amps. That's what equals I0. So pretty much that is my answer. Equals minus 11.014. So anyway, I know that I got kind of strange numbers. And, you know, it's also important to realize, I know that some people have trouble with this. It's absolutely possible that I can get negative voltages and negative currents. You know, I got a negative current here. So it really means that, you know, current is flowing the opposite direction through this resistor. Current through the 7 ohm resistor is actually flowing from the bottom of the circuit to the top of the circuit. So, and that kind of should hopefully gel with you a little bit, but if you just look at the circuit. I've got 2 amps flowing this way, but I've got 7 amps kind of being pushed into this side of the circuit. So it should hopefully, hopefully that should make some type of intuitive sense for you, that really for all of these resistors, not just for my I0 resistor, current is actually going to be flowing from the bottom of the circuit to the top of the circuit. So hopefully, I should get rid of that. I'm going to get rid of those arrows just because I don't want you confusing them, thinking I'm redefining my currents I1, I2, and I0. But hopefully that should make somewhat intuitive sense, that I'm pushing more current into my ground node of the resistor. I'm pushing 7 amps of current into the bottom of the circuit, and this current source is really only pushing 2 amps back out. And really, also, you should also think about, could I have possibly combined those two current sources, or would it have made sense to do that? Anyway, hopefully you found this useful. In the next video, what I'm actually going to do is I'm going to teach you how to use, there's an online tool called Circuit Lab, where we're actually going to simulate this circuit and just try to get these answers out. So anyway, thanks so much for watching, and I'll see you in the next video. And then, I guess in the subsequent video, after I show you the simulation, we're actually going to do a more complicated example. So anyway, thanks again for watching, and I'll see you in a future video. Bye.